So it's 2 p.m. So we can start the second tutorial of the blockchain track. And it's a pleasure to introduce Peter Van Roy for this presentation. But before starting, I have to announce that this presentation will be recorded. So if some of the people that is attending this presentation or object against the recording, please let us know that in that case we will stop it. Otherwise, if there is no objection, we will go. Okay. No objection, so you can start with the recording.
Thank you.
Thank you.
Everything is fine. Everybody can hear me. Okay, welcome. I'm going to present to you the ΔQSD paradigm for system development. Before I start, a moment of silence for the people in Ukraine who are fighting for their freedom and ours. Thank you. ΔQSD is a paradigm, so an approach to a lot of techniques and case studies around it. For designing large distributed systems, you can predict performance and feasibility, whether it's even possible. You can predict that very early on in the design process. This has been developed over 30 years by a small group of people and who have published bits and pieces, but somehow it never got beyond their little circle, but it has been widely used and validated. And it's a compositional approach, and performance and failure are first-class citizens. It also captures uncertainty. You can talk about partially defined systems. And this little tutorial, I'm going to give you an introduction so you get what the main ideas are, the basic principles. There are two main concepts: quality attenuation, called ΔQ, and outcome diagram for describing full systems. And in this tutorial, I'm going to use refinement, performance computation, and you will see what kinds of things you can do with it. I will also show you how to determine infeasibility while you're designing, whether you're actually trying to do something impossible. And the goal is that you will have the concept so you can actually try to start using ΔQSD in your own designs. So the table of contents, I'm going to start with a few case studies. These are large industrial case studies. The names have been changed to protect the innocent and the ones who signed the non-disclosures. Then I will present quality attenuation and some how to design outcome diagrams. I will talk about the Shelley block diffusion algorithm. And I think that's about all I'll have time for. One caveat, so me, Peter Van Roy, I am totally not the inventor of ΔQSD. I am just a computer scientist who's interested in distributed systems and programming languages. And when I saw ΔQSD, I immediately found that this was an excellent approach that deserved to be more widely known. And so this tutorial is still kind of work in progress. It's kind of my experience learning this paradigm. Okay, let me start by giving you a basic fix on the two main concepts: quality attenuation and outcome diagram. Quality attenuation, which usually will be marking ΔQ, it's a cumulative distribution function, okay? Delay versus probability. And it does not actually go to 1. It actually also talks about failure probability. So it combines delay and failure in a single variable that can be handled by itself. And the second thing is the outcome diagram. This is an observation of the system from the outside. An outcome, so we have made formal definition, it's any system behavior that you are interested in that has a start and an end, and of course there is some delay or failure probability, so there is actually ΔQ associated with it, and the whole system is described by an outcome diagram. It's basically a directed graph that shows the causal relationships between all outcomes, so you can use it to compute the ΔQ, so the behavior, the delayed behavior of your whole system, okay? You can also express partially defined systems using outcome diagrams. You don't have to know the whole system. Okay, so that gives you the two, just a snapshot of the two main ideas. Let me now present a couple of case studies, 3 case studies. They are all coming from PNSol. So I'm going to be showing you mostly slides that come from them. So they're industrial case studies, small cells, iPhone launch, and Cardano Shelley. They are kind of limited documentation as usual for industrial projects, but I hope you'll get the interesting lessons from them. ΔQSD is used in two ways. One is for diagnosis. Some big company has a problem and they panic and they say, oh no, our system doesn't scale. And they run to PNSol, and PNSol has to be Sherlock Holmes. And the other use is design. So that's actually the best. So you want to actually use it for design. And that's one of the purposes of this tutorial, so that we want to disseminate ΔQSD so people can actually use it for design. Okay, prevention being much better than cure. Okay, the first case study is what they call the small cells. Small cells are small cellular, small towers for cellulars, low-powered access nodes. So there's a little story attached to this. A major mobile network operator, and they really exist, I know who it is, but I will not give you their name, deployed these small cells. And the system, it seemed to work, but it did not scale. Voice quality had major problems, cells were failing. What's the problem? So PNSol actually looked at this complete system, determined the outcome diagram, and measured delta Q across the system, and led to a successful diagnosis. Okay, here is the schematic of the whole system. It starts here from the user, and at the end there's a reference point. So you go, the small cell here controls, receives things. It goes through the wholesale access network. So this is just some company. It goes through another control point, the national interconnect in the country where this was done, which is the UK. And then it goes to the core of the actual network operator, and there's a bunch of observation points, okay? So the MNO, the company, is combining all this, but they are actually only responsible for a piece of it, okay? They believed that this would work and that there were no residual hazards, means no problems that could be showstoppers, okay? And they were wrong. PNSol then came in, and they gathered evidence. They looked at all the points, A, B, C, D, E, made synthetic traffic to reference points. They added internal observers at different parts, because you want to split the overall behavior into small pieces and delta Q for each one. And so you have then an outcome diagram connecting all of these internal observation points, A, B, C1, C2, D, E, and you measure the quality and attenuation across all of them. Each observation point, they say it doubles, but it increases by a lot the fidelity, the amount of information you get, okay? So just recalling, so this is all, so they put in all these observation points there. Okay. Now, look here at this graph. Here at the top, you have the runtime of the system, the delay. You have, this is going from A to the NHC, so the at the other end, then back to A. So it's basically doing round trip. You can see there's a lot of variability. You have here the upstream and the downstream. Okay, so you see that so this is equal to this plus this. You see the upstream variability is 5 times greater than the downstream. Okay, but actually the problem is not the upstream. So that's just the first step. Who's to blame? We're going to look now at subpaths of the system. So here is upstream. Okay, this is hard to read, but assume this is the upstream on the same scale. The downstream. Notice here something weird is happening. Okay, you have observed delay and runtime of the system. Something strange is happening. So let us focus in it. Remember, the system has the national interconnect, the wholesale, the national interconnect, and then the MNO. So the problem is here. So you go from the national interconnect to the wholesale access core. Notice that there's a problem right here. The delay just goes through the roof. Okay. So why is that? Okay. We zoom in on it. We expand the temporal resolution. You can see here in seconds. Now, what is the cause of this? And this is actually existing in a particular, from C to B, in a particular delta Q. And what is the reason for this weird behavior? In fact, it is a Q overload pattern. Components, system components that accept packets and packets go out, internally, you could model them as a queue in terms of queuing theory. And a queue has a certain rate of requests that is able to treat. And if you go higher than that, then you are overloading it. So you can actually define a load from less than 1 to greater than 1. If you overload such a queue, you have a temporary overload. Actually, because of the queue buffer, this temporary overload has a long-lasting effect. So if I have time, I will explain what's this. Studying queue behavior is the delta Qs of a queue is part of the ΔQSD. So the problem here is a queue being overloaded, okay? And this was a prediction. So we actually, or PNSol actually made a formal mathematical model. This is one of the things we will talk about in this tutorial. And so the queue, the model that the queue was actually overloading corresponded closely to the measured delay. So this gave confidence that they were correctly diagnosing it. And what is the diagnosis? Okay, a queue is forming, which means packets are piling up. They are arriving too quickly to be handled. The arrival rate from the MNO security boundary exceeds the capacity of this XDSL line, temporary overloading. This is actually extremely dangerous because it has a long-term degradation, okay? So that is the problem. The queue delays all traffic, including the small cell control traffic. Remember, there's these small cells there. Notice small cells are known to fail if their control loops exceed the given round trip time. And here we have figures exceeding are 5 times that limit. So it has lots of side effects, including the cells failing, okay? Resetting, system reset. Also, the voice quality is degrading. These small cells, they breathe, so they have these long delays, which are inappropriate. So this understatement, it weakens the business case, okay, which is understatement of the year. Why is this crashing? So let's now take a look back, system point of view. There is an unmanaged hazard. So the concept of a hazard is possible part of ΔQSD, something we have defined that sits with the MNO. The root cause is that the subsystems are not composing, they're incompatible. Prerequisites to their use of one are not met by the other. And this particular MNO believed that only the bandwidths had to match. People are so focused on bandwidth, but bandwidth is by far not a very good way of characterizing components. Delta Qs are much better ways. And the delta Qs is what should be matching, okay, which didn't. So PNSol made recommendations to this company, and companies have what's called a corporate risk register, something that can affect the corporate plan. They recommend technical training, and they propose to demonstrate a solution. So it's not clear how much of those suggestions were actually followed by the large MNO in question. Okay, let me go to a second case study. So you can see here.
Sorry.
Yes?
Sorry. When you say that the subsystems don't compose, you mean you discovered this at the QE network level or which level? I didn't understand this.
Compose means when I take two components together and for example, I connect one to the other, sequential composition. The resulting system should have a well-defined behavior that is determined by the behavior of the two. It should not introduce problems, okay?
Okay, but you did this at the software level or at the QE network level?
I'm not sure. This was on the actual running system that.
Oh, the actual running system.
So we were observing an actual deployed running system that was having problems. Okay. This is not a design. This is observation. There are these problems. Where are the problems coming from? And the problem was that there was a complete mismatch in the composition of two subcomponents, because they were using the wrong way of matching. They were matching bandwidth, which is not the correct way to manage them. Delta Q is much more important, actually. I mean, bandwidth is important, but people tend to focus on bandwidth, and delay is actually just as important, the delay behavior. Okay, but this is just a case study. I go much more. So now iPhone, again, there's a story attached. This is a real thing. At some point in time, there was a single network operating supporting the iPhone. This was some years ago. A second one prepared to enter this market, but the second one, somehow the performance of their system was not good, and this was actually known. And the first one was very happy. They had prepared a major ad campaign focusing on how bad this new one was, okay? So the second one was, of course, panicking a little bit on the day of the launch. And PNSol was able to diagnose and correct the problem just before the launch, okay, which would save the second. And in fact, the second actually had a better performance than the first. So the first was really not very happy in this case, okay? So these are two real network operators who I will not name, okay? So again, observation points were placed. So this is the system of the second. You have internet here, you have a mobile terminal, you have a radio network controller, okay? So this, you basically have to do round trips here. So again, you determine the outcome diagram, the observables from one side to the other and back, and the delta Qs through the different pieces, okay? And introduced where the problem was coming from. Pinpoint the problem and find solutions. Okay, what is the packet delivery behavior? The round trip time from one side to the other and back, the first 100 seconds. Note, this is actually not the real data. This is synthetic data that kind of resembles the real data to protect the innocent. So this sample is not showing any particular problems. If you continue, if you go for 800 seconds, you notice here there's actually a service break. Okay, also enormous delays. This is delay, break, nothing passes here. Okay, excessive delays up to 1 second. Very bad user experience here. So how come? Okay, where is it going? Now we want to focus again. So we put observation points, we measure delta Qs, and there's 3 different colors here. Okay, there's the blue, the green, and the red. Okay, so the red one is the uplink, the MT to the radio network controller, or the mobile terminal to the radio. The green is from the radio, which is in the middle, to the internet and back. And then the blue is the downlink from the radio back to the mobile terminal. Okay? And the MNO had some suspicion that the downlink was trouble spot, because downlinks tend to be problematic. But in fact, no. You can see already the problem occurs in the red, in the uplink. Okay? So the problem occurred here in the uplink. And now I'm going to go very quickly. I'm not going to go. It turned out there were some content filters that were badly configured, which caused some intermittent problems, which improved at this particular part for the uplink. There were some other problems. So there's a whole slew of problems that were fixed. This also, the TCP throughput was increased, and in fact this solved a lot of the problems with this MNO, which actually became #1, and it's not because of any great qualities in there from their part. It's because of the very good diagnosis that was done afterwards. Okay, so these two were diagnostic. The third one is Cardano Shelley. So Cardano is a cryptocurrency, and I'm not going to talk so much, but this particular cryptocurrency has an algorithm called Shelley, which is a part of the Cardano. It's an algorithm which does block diffusion. When a node in a cryptocurrency is authorized to create a block, it has to have the most recent block. So recent blocks have to diffuse across this network in a good way, and also even with adversaries and so on. And in Cardano, the initial implementation, Jormungandr, Nordic-inspired name, was done in Rust language. It was not good enough, so it had to be jettisoned. But they did another implementation called Shelley. This one was done in Haskell, and it's not because it's done in Haskell that it was better than the one done in Rust. There was a bunch of no-brain people who said it must be good because it's in Rust. That's false. The same other set of no-brain people said it must be good if it's done in Haskell. That's also false. It's good because it's designed, okay? So in this Shelley implementation, ΔQSD, the PNSol people were involved from the beginning. So the design was done using ΔQSD principles. And this is the one that is currently running in Cardano, okay? This achieved adequate performance. So this is an example I'll talk more about later in the tutorial. Okay, so those are 3 case studies, 2 diagnosis, 1 in design. What I want is to teach you how to do design. And the first step is talking about quality attenuation. So what is quality attenuation? I have a system component here, a message comes in, a message goes out. How do we characterize what's going on? So we don't care about the content of the message. We want to know, this is non-functional property. We're thinking about performance here. There is a delay between entry and exit. There's also a chance of failure. There's also some jitter. The delay is not a constant, okay? And this is where delta Q comes in. Delta Q is a single quantity that combines these 3 ideas. It's a cumulative distribution function. Horizontally, we have delay, and vertically, we have a percentage. So everything to the left of D here has the delay is less than or equal to D, and we know that there are P% of the messages that have this property. And this is an improper random variable. This does not have to go to 1. There is actually a failure probability that is also encapsulated in this, okay? So the delta Q is basically a cumulative distribution function of the delay that can have an improper end, okay? So that seems very simple. Just attracting your attention on one point. Yes?
It's not simple, at least not to me.
Okay, fine.
Slide, please.
Please.
So I understand the x-axis is delay.
Yes.
Okay, so that's measured in milliseconds or
For example, yes.
And the vertical axis is a percentage.
Right.
And failure is represented as an indefinite delay.
Yes, exactly.
Okay. And jitter, is jitter represented in this?
Well, jitter, this is not representing correlations between packets or anything. It's representing the variation of the delay, yeah?
So that's
delay is not a constant.
On this graph.
Constant, this would be a step function, huh?
I see. Okay, so this jitter is not... Okay,
correlation is a separate thing which is related to resource management. At this level, it's enough to know where the density of the delays are, okay?
Makes sense, thank you.
Yeah, you can of course have more information, and the correlations is another thing, but that comes back. We're assuming that the packets are independent, the first approximation, okay? But then they may not be, and then you have correlations, and that's...
So this is a distribution of the first packet through the network.
Yeah, you can see it like that.
And
yeah.
then just to be clear, delta Q is that distribution.
This is a delta Q of 2 points, 2 observation points, is a particular instance of such. So this is a value, a particular instance of this cumulative.
Cool. Okay, so just to be clear then, the diagram on the top right is a delta Q.
This is just an example of a possible delta Q value. Exactly.
Thank you very much.
Yes. Okay. Yeah, this is not really a theoretical talk. All of these concepts are theoretically founded. But so if you have, any particular questions, then I can, if I understand it, I will go into the details. Huh?
I have another question. Just
yes,
please. So here the delta Q is defined according to these two different dimensions, delay and a percentage of failure. But in principle, you can have as many dimensions as you want, or Just it is limited.
Yes, you are completely right. And in real systems, the delta Q will depend on other things as well. For example, it will depend on the load. The rate of arriving packets may change, the delta Q. It may depend on other things. Maybe this is using a particular CPU core and it's shared between another one. So it may have other dependencies. So this is the default, okay? By default, there is no dependency and dependencies are added later, so when they are needed. So in many cases, this default is a reasonable one, okay? Its experience shows us we only have to add things like correlations and other dependencies in specific cases, which I will come back to.
Okay, thanks.
This is, yes.
Sorry, may I just relate the two? Yeah, so this is one particular delta Q, but there is no need for this to stay constant, even for a single outcome. So that shape of the diagram, the shape of the plot may change over time.
Yeah, okay.
Yeah, the delta Q might be, this particular thing might be also a function of time. So you have to define, of course, how you have to be a little careful in how you define that, because you need some kind of a notion of an instantaneous delta Q that changes over time. So there's you have to be a little bit careful in how you define it, but that actually works in practice. That gives you a good understanding of real systems, okay? But I'm going to go much more into some of these points in a little bit. So just again, to emphasize how it's very important to combine delay and failure. Typically, system designers will consider that separately, okay? Failure being like fault tolerance, okay? But if you combine them, then it allows certain kinds of trade-offs to be much easier to examine. For example, you can trade off failure and delay, even in a simple way. If you change your requirement, you change your maximum delay that is tolerated, you will reduce the failure if you've increased the delay. That's a very simple, that's purely conceptual. Or you can do retrying. You can retry, which will of course increase the delay and reduce the failure. So there are ways to trade off failure and delay, which are all sitting inside this delta Q thing. So the delta Q is a very good starting point. And I think you have good questions that it's not telling you everything, but it's a very good place to start. And there's a lot of mathematics that you can define around them. For example, you can define they are a partial order. The blue one and the black one here. So the blue one is less than the black one. It's everywhere to the left and above. Of course, they can also intersect, and if they do, there's no order between them. Okay. So now let's start designing. What I want to show you is how to design with delta Q. We want to use delta Q to help design. I'm going to start with a very simple system, just connecting two components, so simple. And I'll show you both a top-down and bottom-up design. Start with the bottom-up. The top-down is actually the more interesting one. I'll also show you how you determine infeasibility. When you're designing a system, how can you all of a sudden see it's impossible, okay? And I will, to do back of the envelope calculation, I will assume a simple form of delta Q. I will assume a uniform distribution, okay? But in fact, that may seem very simple, but in many cases that is reasonable. Okay, so I will present many distributions in this tutorial. The first one is the uniform one. So basically there's a minimum delay, a little a, and then there's a spread and a maximum delay, a plus the spread. And so there's an equal percentage of any delay between the minimum and the max, okay? Nothing below and no delay above. This actually, to a reasonable approximation, many components are kind of obeying like that. And this is actually a useful way of doing back of the envelope computation. Of course, an automated tool that would use delta Q would not care about this, but it's important to have both. The tool can do an arbitrarily complex delta Q, but the engineer who loves to do back of the envelope has to do back envelope, and so the uniform is a good place to start. Okay, so here's a very simple design. I have a component A, and I have a component B, and we connect them together. That's it. And A has a delta QA, B has a delta QA, and what is the delta Q of the combined system? Okay, in some sense, I will say we add them, but in fact, we are doing a convolution. If you want to be very technical, we're taking the derivative of each of those to get the density, then we do the convolution, and then we integrate again. But this is, I will say that we're doing a convolution here, which corresponds to sequential composition. And in the case when the delays are numbers, it is addition. So it's generalized addition. In the case of uniform, we can actually get some back of the envelope numbers. The overall delay, QC, delta QC, is actually a little bit more than the minimum of those two because of the spreads. And the overall spread is actually determined by the one that's the worst of the two. It's in some sense the max. That's what the back of the envelope teaches us. So this is very simple, right? It gets much more interesting when we do top-down design, okay? So in a top-down design, here we have a global requirement, delta QC, and we know component B, and we're designing the system. So we have to find out what are the requirements on A. And we're doing a top-down design. We know C, we know B, and we have to say, which off-the-shelf thing should I buy to plug in here? And so in the equation where delta QC is delta QA plus delta QB, the unknown one in the red here is one of the arguments. Okay, what delta QA is needed? Again, you can do the back of the envelope computation to say what is the minimum delay and what is the spread, okay, using the approximations for uniform. Yes?
I can't stand the suspense. Is delta QA uniquely determined by delta QC and delta QB?
Well, it's deconvolution. So in some sense, I think, so okay, I think that in many cases it is, but not always. But you have to look at what are the properties of deconvolution. I will talk a little bit about deconvolution. The way to do deconvolution is to transform from time to frequency domain. And then you do the subtraction or the division or whatever, and then you transform back. So how unique is that? So there's a problem of phase relationships. So I would say it is, but there are some side conditions, but I'm not a mathematician.
That's a clear answer. What you said is this is a known problem and it's called deconvolution.
Oh yeah. This is a huge amount of literature. It's highly computationally intensive. So it's doing this inverse convolution, and it's in fact, the problem, it's not so much the unicity, the problem is that you actually lose information. This is used a lot in areas like seismic tomography. Tomography is a typical example where you have to do deconvolution to find out what's inside of your brain. And so there are limitations on how precise you can be, okay?
That's a clear answer, thank
you. To just paraphrase that, can we say that the worst case of the delta QA is uniquely determined, and anything better than that?
That's a requirement. What I'm determining here is the worst case.
Okay, perfect.
And so any one that is better than this is good. That's actually a very good point, and I'll get into it. There's two things I want to. This example is good because I will introduce infeasibility now. Now, component A is only feasible if the delay, the minimum delay, is greater than 0, obviously. You cannot have a negative delay. If you plug this in, this puts a condition on B is less than C minus the minimum of the two spreads, A and B. Notice this is actually a recursive equation because B and B are on both sides. But this minimum is usually quite small. So now we have back into the envelope again here. So basically it means that if B is already slow, then no A can fix that, okay? So there's some constraint on B, the one that we know, so that there is actually a feasible A, okay? If B has a large spread, so if B has a large difference between min and max, that makes things very bad, okay? Because that will make that the M is very large, So that would put a lot of constraints on B. So it's actually, depending on B, A is or is not possible, feasible. Okay, so this is a back of the envelope, approximate calculation. And notice that software, of course, will do the precise computation of deconvolution. So I just want to say a few words. I'm not actually going into the mathematics of it. That would be a whole different talk. So this is, I say it's subtraction, but in fact it's deconvolution. For hand computation, it's incredibly difficult, basically impossible unless you know a lot about the distribution, but it's not a problem for a software tool. So we're taking advantage of the large power of computers and letting them work for us. Okay, and there's another subtlety comparing the bottom-up and the top-down designs. In the bottom-up, we're computing the known behavior of the overall, of the system, of the components. So if the spread decreases, it's getting better, whereas the top-down, we're actually computing a requirement. So this was on the component. So if we decrease the spread, that makes it harder to satisfy that requirement. The real component has to have that's the maximum. Okay, so there's an important difference between bottom up and top down. Understand?
This is a good point to actually relate to your question. So Neil and Peter, the PNSol partners of ours, they have very good intuition about how they do these, and they have tricks to actually make sure that they can very quickly get very well defined functions for that, even though they don't quite do the job of doing the intense, the computationally intense.
So they have heuristics for solving these deconvolutions.
Yes.
Yes.
Might not be optimal solutions.
Yeah.
Then. Okay, thank you.
That is good enough.
Yeah.
So they can, and Neil is here himself, so he might, I think he raised his hand, so, okay.
So Neil has raised his hand. Neil, say something. Unmute yourself.
Okay, can you hear me?
Yes.
So actually, these systems form a linear set. You can do it in a linear way, so you can use Laplace transforms to get something that actually helps you control this process, right? So it's possible to do certain properties like median and variance and min and max very cheaply arithmetically while you're doing things.
Okay. By the way, Neil is one of the originators, so very technical, and he's also mathematically quite good. So he probably knows more about the mathematics than me, for sure. Okay, now I want to talk about the second step. Delta Q is just, it's like when you're building an electric circuit. You have resistors, transistors, but then you have the whole circuit, okay? So the outcome diagram is a way of defining the whole system, not just a single component. We'll combine these components, which are defined by delta Q, into full systems. And the outcome diagram is the concept that helps us define that. And an outcome diagram basically defines the system by looking at the behaviors from outside. It's purely observational. In that sense, they are completely different from all the different variations of UML diagrams. A UML diagram is always telling you something about the system structure, okay? Carefully, it's always, even partially, saying something about how the system is built, whereas outcome diagrams do not say anything about how the system is built. They say purely what you observe, okay? And many kinds of components, of course, can be brought together and described in this way, software, but also humans or mechanical systems, okay? And as we'll see, we've seen already a little bit, performance and feasibility can be computed for these outcome diagrams, okay? So let me start with the beginning, the simplest base case. We have, again, a single component, some kind of server, a query comes in, and a response comes out. So this is an actual running system component. This corresponds to an outcome. Assume that we're interested in the query response behavior. Then the pair query response is actually outcome. So an outcome then is O1 here would be a pair of these two. And in this, I will always use these orange diagrams for outcomes and the blue ones for actual concrete systems, okay? So an outcome is a specific behavior which is defined by a start event and an end event. So that is pretty close to the formal definition. We're observing the system, okay? And there's the causal connection. So it's a pair. In some sense, R1 will be caused by R2, okay? So this is just an abstract view of what the system on the left is doing. Combining now, so again, the little example where I'm connecting two running systems, user click to browser causes query to be sent to server response to be sent back, okay? The outcome diagram corresponding to this is a graph showing the causal connections. There's two outcomes here, the user click causing the query and the query causing the response. So we have two outcomes. Each outcome has its delta Q, and there's also an U1 R1 is also an outcome. Any two pairs that are causally related could be defined as an outcome if we're interested in that. So this is describing the behavior of the system, okay? Okay, these two diagrams, they look very similar, but we're going to see examples where they start looking more and more different, when the behavior of the system does not always follow exactly how it's constructed, okay? A few little nitpicky details on how outcome diagrams work. This diagram here, this orange diagram, these boxes and circles, they are actually potential events, potential outcomes. You can consider it more like classes and not objects. So you could have an event occurring in this little box, the first orange box, event U, event Q in the second one, and that together they form an outcome O1. But you could have later on another event, U prime occurring here, and another Q prime, you would have O1 prime. So you can have many outcomes corresponding to this diagram, okay? So this diagram is in some sense a template of potential outcomes, okay? And in real systems, this will happen often. If you have many packets traveling through, you will have many occurrences of outcomes with events and that are appearing at the same locations. The boxes here are called locations. This is potential place where an event could occur, okay? So all of this is part of the formal definitions. It's all much more precise in the formal definition, but I will not go into the real formal definition, okay, here, but I will show more examples. Here's a simple example, and this outcome diagram is pretty straightforward. We have a browser, a network, and a server. You're buying something from Amazon, so user click, query created, query sent, query received, response sent, response received, response processed, response displayed. This is just a sequence of causally related outcomes, okay? Each of these has its own delta Q, and the overall delta Q is just the sum or the convolution of all of them. Okay, so that's very simple, and you might think, well, outcome diagrams, they're like pipelines, but they're not like pipelines, as we will see. First of all, let me now take a step back and talk about general system design. How do you use this approach in designing systems? I want to build a system. I'm a big network operator who is doing things correctly, and I want to build a system and does not need to bring in PNSol to fix it afterwards. So I start with an unknown system. So this is the gray circle, and I refine it. This also we have formally defined it. So this gray circle becomes a part of an outcome diagram. There may be more unknown subsystems in there. And the interesting thing is that for each of the orange circles, we can know the delta Qs. We may also know the overall delta Qs, and we can use the approach of the top-down design to figure out what would be the requirement for the unknown ones, the gray ones. And eventually, we end up with a completely defined system, which has only orange ones and no more gray ones, okay? But during this whole process, at any step along the way, we can compute a predicted performance and see whether the system is feasible. Okay? So here's how it would work in top-down way. So this is the same picture as in the middle of the previous slide. I have a request and a reply, but there's some unknown system in there, some database, for example. The system delta Q is the sum of the request, the unknown, and the reply delta Qs. So these three are known. This one, the red one here, is unknown, okay? We can compute it using deconvolution, okay? And we can actually see whether it's feasible or not. Now, if it's infeasible, then we made a mistake somewhere in our design. We have to go back. Maybe we did something wrong here in the request. Maybe we changed the request and the reply, and then we recompute and see whether delta Q unknown is feasible again. Maybe we are completely messed up and we have to go all the way back to the overall system requirement, delta Q system, and somehow we have made an impossible requirement. And that actually happens more than you might think. For example, the delay of a telephony system, anytime you add a component in a large telecommunication system of telephony, you will be increasing delay, okay? The lowest possible delay ever seen in a telecommunication system was the system built by Alexander Graham Bell, believe it or not, because you had a microphone, a wire, and a speaker, and nothing was increasing the delay. Whereas now, today's systems, you have all kinds of sophisticated stuff in the middle. That is not necessarily an improvement. That is pushing you towards infeasibility, okay? So this actually happens much more than you might naively believe. The infeasibility happens a lot. The Alexander Graham Bell story is coming from Neil. I thought that was a very good one. So the whole design process, so here, each of these little blue circles in this tree here is a partially designed system. You start with an unknown system here, you make a design decision, so you follow a little arrow down, and these little arrows, the Ds, are design decisions. So you go down, eventually you end up with a completely designed system, okay? Here, for example, in this left subtree, you have a whole bunch of completely designed systems. Unfortunately, they're all infeasible. You try to build it and you see it doesn't work. Whereas in ΔQSD, you could already see here, after doing dx, that it was infeasible. So the advantage is that you can detect the infeasibility very early on, using the technique I showed in the example before, okay? So the whole design tree here is actually navigating up and down, and at any point here, you can detect feasibility, infeasibility, projected performance, and so on, taking into account many things, load, congestion, correlations, that can all be taken into account here, okay? Actually, one of the things that struck me on this is that it's very similar to a logic programming system, okay? Where feasibility corresponds to satisfiability, okay? Actually, I think the connection is pretty strong. At each point for a partially defined system, you could consider that to the model of that, in the sense of logic, to be the set of possible systems that are consistent with that partially defined system, okay? And then this is basically just doing logic programming. I thought that was a very interesting, it's a very interesting correspondence. Okay. So this has been, to some point, formalized. So the person most involved with that has been Hossein Hayri, but this is an ongoing project between us and PNSol. There are, in fact, many more than just sequential composition. There's probabilistic choice and last to finish, first to finish. So we have a formal language and a semantics for computing between the delta Qs. So I won't go too much into that, but I will give examples, okay? So here's an example, cache memory. This one is interesting because it's using a probabilistic choice. So here in the left, we have a cache sitting in front of a main memory. The processor does a read. You either can have a hit in the cache, you immediately return, or you have a miss, and then the read has to go on to main memory and then return, okay? So in the refinement diagram, you have here a read operation, but it's refined as follows. Here, this is a new operator, which I haven't shown before, called probabilistic choice. What this means is that between these two events, read and return, in the actual system, either you will have this outcome be realized or this outcome. Here I have a sequential composition. So you have here either a hit outcome, 95% of the time, or a miss outcome, 5%, but the miss is then composed with a main memory read, okay? So the probabilistic choice here, then of course we are not modeling how the things are stored in this cache. We are abstracting away from that. It's a pure probabilistic choice, and the delta Q of the mem outcome can be computed from the 3 other delta Qs using the probability of the choice, okay? And here we are just doing a sum of delta Qs, okay? A weighted sum of the 2 delta Qs. Between the miss and the main, it's a convolution sum, of course. So that's an example of probabilistic choice, and you can show what happens in terms of the actual delta Qs. So assume you have 95% hit ratio, it takes 1 cycle. The miss takes 1.5 cycles to figure out and forward. The main memory read takes 4, just numbers I plucked out of the thin air. And if you combine those 3, you get the actual delta Q, which has this kind of a step function of the actual memory behavior, okay? So things like cache memory structure can be well modeled using this kind of approach. Okay, let me now move on. Let me go back now to this block diffusion algorithm, this crypto algorithm, and to show how the ΔQSD can help in the design of this. Okay, let me give you a little bit of context. So I'm not mainly doing cryptocurrency. I'm agnostic on it, although in terms of distributed algorithm, it's very interesting. So in terms of the Cardano cryptocurrency, this is all work that has been done in that context. And this solves a problem in Cardano, okay? So a blockchain, it's a distributed ledger, it's a set of data blocks, witnesses corresponding to these transactions within a very robust consensus algorithm, okay? In Cardano, this is called Ouroboros-Pearl's consensus. And this consensus algorithm will randomly select a node to produce a new block during a specific time interval, okay? And it does proof of stake, so it's weighted by distribution of stake. So that's all precursor to what I'm going to talk about now, which is the Shelley block diffusion algorithm. The block producing node, the node that's been chosen, needs a copy of the most recent block to produce the next block. Therefore, the most recent one somehow has to be diffused over all block producing nodes in real time with all kinds of constraints. So we need to design a block diffusion algorithm that is adequate for this and satisfies the timeliness constraints that are needed, okay? So this is what I'm going to talk about, or part of it. Fully talking about this algorithm would probably take several hours, so I'm not going to talk about it. There's a paper that I will mention later on that has more information. So the problem statement, in the simplest possible way. Here we have the node graph of the Cardano blockchain. So this node graph is changing over time, okay, directed graph. We have 2 randomly selected nodes, A and Z. And the problem statement is determine the delta Q between A and Z as a function of a number of design decisions we make. Also determine these decisions so that delta Q AZ satisfies certain performance constraints. And what is known is delta Q XY. So for 2 nodes that are neighbors of each other, we have measured the delta Q here. And there's a number of design decisions to be made here. The frequency of block production, the topology of this graph, the size of the blocks, we're talking about real network protocols, the actual forwarding protocol, the processing time on a node. So these are some of the most important things. So I will talk about some of that, okay? So first of all, just an overall picture of the design process. So this is a complex system with a huge number of constraints. So the design process is going to be somewhat elaborate, okay? So it's in 2 steps. a preparation step and a actual design step. The preparation step, you need a certain amount of preliminary information, an initial simple design and its outcome diagram. You also need to measure the delta Q in actual reality, which I'll explain. And the second step is where you actually go through this design tree that I mentioned before. So this here is the tree, but kind of collapsed. I have an initial one-hop designing. I'm assuming that all the nodes are neighbors. Okay, I'm assuming now that I will do multiple hops, so kind of routing. I'm assuming now in the next step that I will split a packet into a header and a body. And that can by far improve efficiency because the header can be much smaller than the body. So when I want to ask permission to get a block, I only have to send the header for that. Also, the topology will depend on the real world underneath, and nodes may want to join other nodes because they have a good connection, a fast connection. So the topology is changing. So there's this rejoining protocol. There's also a neighbor selection. At some point you will select neighbors because they have a fast connection, for example, okay? So each time you make a decision, you will compute what is the estimated performance, whether it's feasible, and if it is, you keep going. If it's not, you have to go back and change the decision, okay? So this is actually explained in some detail in a paper that we recently published called Mind Your Outcomes in this magazine called Computers 2022. So you can find that, and it has much more explanation than what I'm giving you here. Okay? So the first step is to measure the delta Q. And this also requires some outcome diagram reasoning. We have different block sizes, 64 kilobytes to 2 megabytes. Network speed, we're measuring the speed. Geographical distance, we're assuming 3 levels, short, medium, long. And the congestion, we're assuming we're initially ignoring congestion because we're talking global, but it can be added later, of course. So what we do is we start with single hop delta Qs to neighbors. These will approximately be step functions. Then we compute multi-hop using sequential composition, which is convolution. And then we will compute random path, because when I go from one node to another, it's not always the same number of hops. There may be paths of different lengths. So you have to make a weighted sum and use probabilistic choice. Okay, so this is all computed using the outcome diagram. So here's some of the results of this part. Here in the top is the one hop delta Q per block size. So the different colors are the block sizes from 64K to 2000K. And you can see here the transfer delay and the cumulative probability for the small, medium, and long distances. So the steps. Now we compute multiple hops. So we have 1 hop, 2 hop, 3 hop, 4 hop. So the 1 hop is the step function. 2 hops is a little bit smoother, right? Because now we're going to 2 with 1 intermediate node. We go up to 5 hops here. So on the left, we have it for 64 kilobyte nodes, packets. On the right, we have it for 1 megabyte packets. So you can see it kind of smoothens out when we increase the number of hops. So this is determined. So this is measured. This is determined using convolution. And then the final step of the measurement is the varying path lengths. So we assume a random graph of 2,500 nodes of degree 10. This can be changed, of course, and we compute what are the weights of the different path lengths, and we make a weighted sum, and this gives us then the final delta Q for the path lengths, the raw delta Q between 2 randomly chosen nodes, okay? Notice each of these delta Qs is already giving a lot of information, Remember, I have to remind myself that CDFs are actually already giving a lot of information. So that's the first step. Let me now give you a piece of the second step. Okay, so the outcome diagrams start getting complicated. This is the one I will explain to you. This is, let's say I want to obtain 3 blocks from the fastest neighbor, where blocks are divided into header and body for efficiency, and I need to get permission before the block is transmitted. So in order to get a block, I have to ask for permission first. Why? That's because the way blockchains work. You have to ask for permission first. Okay? And so this is part of the design process. Okay? So this will happen, of course, repetitively. Yeah? Each time you make a decision on this, taking something from the fastest neighbor, I'm dividing block into header and body, I will get more and more complex outcome diagrams, okay? So the one step I want to explain here is obtaining several blocks from the fastest neighbor. So assume that we've decided that that's the right way to go. First, let me show you quickly the two operators that I have mentioned, but I have not used so far. This one is called all to finish. It's with this little for all symbol. So I have a number of outcomes here which are alternatives, and the Z plus outcome event occurs when all of these are finished. So all to finish, okay. Then there's the first to finish, the little outcome at the end here, which is not written because I've basically took this diagram from the paper, but there should be a little square here, is finished when at least one of them is finished. This is called first to finish. Combining these two, I can show you in a fairly complex diagram how this whole thing works. Okay, so here I want to obtain 3 blocks in order. This is, I need to get a permission request before transmission. So I have permission transmission of the header. And then I go on, permission transmission for the second block, permission transmission for the third block, the header. Those are 3 headers in causal order. Now I have to also obtain the header before the bodies, but only the headers are causally connected, the bodies are not. So once this header has been transmitted, I have to get the body, and this is where this first to finish, this rectangle here, this is, it's a first to finish because I'm interested in the fastest neighbor. Only one of these is important. And here again, the body for the second neighbor and the body the second block and the body of the third block. So the full diagram gives you all the causal connections between the outcomes for obtaining 3 blocks in order, given the design decisions we have made, which is permission before transmission and header before body. Okay? So that's one of the design decisions. You can see you really don't want to do that stuff by hand, okay? For this diagram, you can compute the actual delta Q of this. Of course, you probably don't want to do it by hand, but it could be done by hand. You could even do the inverse thing. For a requirement, you could say, what is the required delta Q for the permission request, for example? You can see the kind of complex what-if design questions you can ask here. So, right, you see this is nice, huh? So this kind of stuff convinces me, yeah? Okay, so this is one of the sub-outcome diagrams. This correctly models the causality and performance of block transfer for 3 blocks. You can compute delta Q, I say easily. I mean, easily means there's no conceptual difficulty. Of course, a software tool would have no problem with this kind of thing. It's one of the reasons why we're interested in making software tool for this.
Sorry?
Yes.
I have a question. So
Sure.
when you say first to finish or last to finish, you mean that you are computing the minimum or the maximum of the
Yes, actually.
functions, right?
That is correct. So it's more like an and an or. So if you, it's in some sense it's a max and a min. You have to combine the cumulative distribution functions, and here it's the earliest one, and here it's the latest one basically. But it's in some sense, if they are intersecting, it's the latest in all cases.
Right.
Hossein can say more maybe.
Yeah, if the resource of interest there is timeliness, then you're right, it's min and max, right? But if you're speaking about, for example, memory, then it's not the minimum and maximum, they will be just added up together, right? And then they can be truncated as soon as the first of them arrives, so you can kill the rest of the process but if it is, for example, all to finish, it means that you have to consume all the memory through, right? So that depends on the resource of interest.
Okay, thank you. Let's look.
Also, I also have a question. Like, why are you using the all to finish operator in this case? Because what you care about is obtaining three blocks, right?
blocks.
So I would expect that you care
Yes.
that you're interested in getting the header from the fastest neighbor, as well as getting the body from the fastest neighbor as well. Why do you? Who has to wait for all neighbors?
No, the thing is that the header and the headers are very small.
Yeah.
So you don't have to usually worry about the transmission speed. The
Still,
headers and the bodies can come from different blocks in the header, of course.
True.
So, but the three headers are causally connected, and if you're looking at each block, the body is causally later than the header, of course. So you have this causal link here, here, and here. You also have the causal links between the headers.
True, but still, why? Who's interested in who sets the requirement to send the header to all downstream peers, or for a downstream peer to receive the header from all upstream peers? Like this for all symbol confuses me a bit there.
Okay, the all
Why do we have a
means that at
requirement?
this point I have got the permission for block one.
Right.
So I need the block one, the body. I also need block two. There's two links here. I need the body of block one, but here I'm looking at the case where I want to obtain three blocks in order.
Right.
I know that there are three blocks and I want to obtain all three of them.
Right. Okay.
I think
Hussein, maybe you.
I can answer that question from a different point of view. The thing is that you spoke about the fact that we know that one of the neighbors is fastest, so why should we just not always go to that? The thing is that that can change dynamically, and the fact is that if you rely too much, so there is gossiping going around, right? If you rely too much about on a certain clique of nodes, then you might get into divisioning the network and all that, right? So IOHK has heuristics for this, and it's kind of split 50-50. So you want to go to your fastest neighbors as well as people who are
random.
Yeah, random.
Yes.
And so the easiest way to put that into ΔQSD is that you would say, okay, I'm going to close my eyes on this entire algorithm. I'm just going to say that, okay, I'm going to get it from everyone. This is an upper bound.
From everyone, but not requiring that I get it literally from everyone, but from the first among everyone.
No, well, you're speaking about you're speaking about, right, Neil was
Speaking about the bodies or about the?
Spirios, I assume that's you. I'm hearing.
Yeah, that's correct.
Yeah. The answer is yes. So the point is that you're conceptually asking everyone for it, or a subset of everyone, and you're just taking the first one you get. Okay. This is not. We're not looking at resource bands on the communications here. We're just saying if this was a model, makes sense, right? And so the first to finish synchronizations are on each of the block downloads, and the last to finish stuff is I need the headers in sequence, right? And then the final thing in the top right hand corner here is that is the last to finish of all those blocks being downloaded. I can now proceed.
Okay. Yes. So you get everything in order. Yes.
Well, no, we have everything so that we can proceed. Whether we got them in any order, I mean, if you imagine that the first block was 10 megabytes and the other two were 64 kilobytes, you could very well end up, getting the other two blocks before you got the first block.
Yes.
Yeah.
True.
Okay, and the fastest of which, when you speak about, are those triangles, the red triangles, sorry, not triangles, the red squares on Right, those are the first two issues,
Yes.
right, that you was.
These are the first to start.
Okay,
Right.
okay. Okay, thanks.
Yeah. Okay, I'm only explaining it partially, yeah? There's a lot more detail in the paper, okay. So this gives us a part of the outcome diagram. Okay, now let me step back again and show you some information about some typical delta Qs, some typical distributions. And of course, a tool can compute arbitrary ones, no limit. But a good engineer has to know back of the envelope a bit, So let's give some theory and some intuition for the common ones. And here's a nice comparison. So we have on the top a Gaussian distribution. So this guy, it basically approximates the sum of many independent random quantities. Central limit theorem, we have a mean and a standard deviation. So this is good for computing aggregates. But this is actually very bad for single components, okay? Whereas if you would have an extremely long pipeline of 100 components, then the whole thing would start to become Gaussian, but usually you don't have that. The uniform distribution is approximating a component where you have a buffer and a server. So you have a minimum time spent there, and you have a spread, okay, of times. And this is actually much better for single components. But let me go a little bit on detail on that. And for queuing theory, so typically arrivals are exponential. So we have this, here you wait a certain time tau, and then you have some exponential distribution with an infinite tail. Okay, so in queuing theory, you always have these, you very often have these exponential distributions, okay? But in fact, this is really not that good for real components. It's good for queuing theory. The problem is that this infinite tail is really not what a real component does. It's usually there's a maximum. And usually the wait time here, it's actually going to be approximately a constant. So this thing is actually fairly reasonably approximated by a uniform distribution for a real component. Okay. And we can now show how you do convolution, deconvolution. Of course, for Gaussians, this is incredibly simple. Okay. The convolution of two Gaussians is just a Gaussian. And you're adding the means and you're adding the squares of the standard deviations. You're adding the variances. Okay. So I'm not going to say much more about that. Let me go on. Uniforms, this is back of the envelope country. Okay, for each of these uniforms, I have a minimum and I have some maximum. So I like to talk about the spread, the difference between the min and the max and the minimum. If you make a convolution of these two, it's not a straight thing. You have this curvy thing. But it turns out this part of the beginning is actually very small, and so it is in the end. So this is actually approximately, again, a uniform. And the spread here is actually the max of those two. It's very funny. And the starting time is the sum of the two, of course, the two delays, but a little bit more. You get a little, the spread of the other slows things down just a little bit, okay? So this gives good intuition for an engineer. Okay, and let me now go a little bit to queuing theory. Now we're going to step into queuing theory and model components and get to delta Qs from that. So here is a queue, and I'm going to show you what the inside is in a minute. So a typical queue, as we're going to study, has 4 parameters that we're interested in. The offered load, A, this is the arrival rate of packets divided by the service rate of messages or packets. So if the arrival rate equals the rate at which you can service them, then the offered load is 1, okay? If it's less, then it's a half. But if it's overloaded, if twice as many packets come in than you can service, then the load could be 2, for example. You also have a buffer internally, buffer size K, and then you have a failure rate. Queues can drop messages, and also a delay, how much time is spent in here. So these two are actually connected to delta Q. Okay, so that's the start. Now, queuing theory. Okay, I'm not going to show you all the formulas, but I did all the computations here. So this is what's known as an MM1 queue. So queuing theory is a whole area, a whole discipline, okay? So this is one particular kind of a queue. where the arriving messages have an exponential distribution with rate lambda. The service time, so here I have a server that can serve a message at rate mu, that's how many per second. It can serve one message at a time, and I have here a queue of size or buffer of size k minus 1. So the total buffer size is k, or the number of messages that can be stored inside the queue, okay? The offered load, what I mentioned before, is actually lambda over mu, the arrival rate divided by the service rate. Now, there are two knobs we can vary to make this thing change behavior. It's the offered load, we control it, how often a message is coming in, and then there's the buffer size, how big this thing is, okay? And it's actually some very interesting intuition there. And for this queue, the MM1 queue, if this buffer here is full, new arrivals are simply dropped, okay? That's the formal definition of a MM1 queue. Okay, so the delta Q is going to be a function of the two knobs, A and K. So what can we learn here? Actually, there's very many interesting things we can learn. And here is the most interesting one. The offered load is a very important parameter here. If A is less than 1, then you're very fine. The component has enough power to serve some messages. If A is greater than 1, the component is overloaded and performs very badly. Now, what does that really mean? It turns out the real threshold in practice is not really 1. It's more like 0.8 or 0.7. And I actually looked at it for a certain number of values. So low load has to be significantly less than 1. If you do that, the failure tends to 0 and the delay will tend to be 1. Okay, because you have 1, the service. So this behaves very well. High load is when it gets at least to 0.8, okay? Or when it gets close to 1, it gets really, really bad, okay? The failure rate, once this increase goes up to nearly 100%, of course, the delay also increases very quickly. When A is equal to 1, you'd think that, yeah, this is fine, right? 100 messages per second come in and I can handle 100. But no, they're exponentially distributed. So the delay is K over 2. Half of the buffer size can be huge. Now, there's actually an enormously fast switchover, like a phase transition between 0.5 and 1. If you actually are configuring a real system, a good rule of thumb is never let the load be greater than 0.5, okay? Even temporarily. And that was the problem with the small cells case study. A temporary overload causes a long-lasting degradation. And the reason is that the buffer fills up and it takes a long time to empty again, okay? Especially if the buffer is large. So even a temporary overload is very bad. And because of exponential distribution, you don't have to be very close to 1 in order for that to happen, okay? This is an important base premise for ΔQSD. You have to understand this. And there's also a buffer size, and here we go into marketing territory. Yeah? The buffer size, how many messages can be stored in a component? So manufacturers love to say they have big buffers, but be careful, okay? For low load, big buffers are actually quite good, up to a point. I mean, if the load is low, the buffer size actually does not make that much difference. It slightly improves the failure rate and slightly improves the delay. So this number gets slightly bigger but close to 1, okay? Bigger buffers are a little bit better for low load, but for high load, big buffers will kill you, okay? If even temporarily, the load gets to 0.8, it gets really, really bad. So a NIC, so a network interface controller, if you can store 1,000 packets in the buffer, and they love to have big buffers, then you better be sure that there is not even a temporary overload, or your system will die, okay? So that's an important piece of concrete knowledge that you have to know, okay?
You have seen these in action in your simulations, right?
Yeah, of course, we've seen it.
Although we don't use exponentially different exponential arrival rate of blocks.
Oh, I see. Okay.
But but I see what you, yes.
But this happens, I mean, this happens in real life, okay? This is an idealization, but it's a pretty good model of, the lesson is true, even temporary, very bad. Okay, there's also the delta Q for a network, which I can talk about. So now I am not having a component doing computation, I have a network delivering packets. So the delta Q is actually a different thing. It has three parameters, G, S, and V, and it looks somewhat differently. So basically there's a component delta Q and a network delta Q, which are fundamentally different, and it's something the engineer has to worry about.
Peter, I think we,
there was a question at the very beginning that the gentleman sitting over there asked about the delta Q having different dimensions. This is the point where that comes.
Yeah, I actually don't have so many slides. You mean what happens? Yeah, there's so the delta Q having different dimensions.
Yeah, this is where that comes in, I think.
This is one example of that.
Yes.
But there was another example where the delta Q is actually a function of load.
Right.
So the Q already shows that, but there's also examples. If you actually try to solve a system where the delta Q is depending on load, it's not a simple, straightforward computation. You're actually solving simultaneous equations. Which is not technically, I mean, there's huge literature. It's just that it's kind of harder to do by hand, okay? But for a tool, it's not really a problem. But it becomes solution of simultaneous equations. Anyone who has done electronics knows what it means. If you want to bias a transistor, you're basically intersecting curves, okay? So it's kind of like that, okay? I think of it as a kind of a biasing issue. What is the stationary behavior? Okay, and then there's also for network packets, but now I'm getting close to, maybe I don't want to go into too much detail. So we're sending packets over a network. Each of these little crosses is a packet. So here we have elapsed time, and we're sending packets, and this is the delay. Each time a packet arrives at a certain time, we put a little cross there. But it kind of looks weirdly random, okay? So you sort it by packet size, okay? The observed delay by packet size. And then you can see there's actually three things. There's the time that's needed for packets of size 0. Here on the horizontal, I have packet size. So here is the delay. So there is some time minimum, speed of light or whatever, the geographic delay, G. Then there is what PNSol calls the serialization or size delay. The delay goes up when the packet size increases for various reasons. Packets are serialized, for example. Also, they are bigger on the network when they have more parts. And the final one is the final fluctuation. So this is coming from a number of things. Why is there this funny little fluctuation? Well, I mean, we're talking about the real world and an electronics system, and there's always noise and funny effects. Okay, so this gives you three final things, for example. Okay, the rest of the tutorial is still work in progress, unfortunately. I have here.
Take this opportunity to ask.
Yes.
Make a comment. So one message at a time. Thank you. One message. Thank you for the wonderfully clear talk so far. One message I'm taking away is that we have an algebra of truth values, and we have connectives, and the truth values are distributions. These delta Q distributions,
right?
Which is great. I love it. These things turn up in lots of places, but some of the things that we're showing remind me actually a bit of quantum mechanics.
In what sense?
Well, I don't know how convincing this will appear, but in quantum mechanics, you have a particle, you don't know where it is, and then you observe it, and it'll pop up somewhere, and where it pops
You have a probability distribution.
Actually,
It's a density function.
It is a density function. It's not just that, it's the way I see you come.
So a delta Q is also a kind of density function. And whenever a packet comes, then you observe it. So it kind of summarizes. So it's analogous in some sense to a wave function.
This is the
Exactly. But in addition to that, some of the ways I see, some of your connectives remind me of the way some of the things some of the connectives I recall from quantum mechanics.
Okay, but that's very interesting. If you have any kind of reference, anything on that? Anything?
Sure, offline.
Please send it. I'm interested in that.
Neil wishes to talk.
Neil?
Yes.
It's actually not, given my colleague Peter did work on rotating black holes at Oxford, in quantum mechanic terms, your observations are very correct. I mean, we have stolen those ideas. I mean, you can think of the delta Q as effectively the Bayesian probability of something happen. So it's like something that, and when you sample it, you collapse it to a particular value. Yes. Yeah. So yes, I think there are some interesting analogs
to it already. Okay. Thank you, Neil.
Yeah. I know. Yeah. Rotating black hole. Anyway, yes. I think the answer is yeah. There's a lot of I think the most interesting part of this is the combination of loss and delay into a single variable, and suddenly, as long as you pick your mathematics carefully, there's a massive amount of literature you can use. You've got to be careful how you choose your basis of measurement theory and how you do your stochastics. But actually, as long as you know the axioms of the basis of the beliefs of the approach system you're taking, you can pull lots in off the shelf. It's interesting.
That's
a lot
great.
more to be
Thank
done.
you. So my follow-up question is whether you observe diffraction in these systems.
That's interesting. Good question.
That's no, actually we don't, because we
Not
per se. I don't think we. I don't think we.
Are you sure? On your own.
I'm
you showed a spike. Do you remember that spike? And you said you'd run a model. And
yeah, but the spikes tend to be coming from things like the central limit theorem, right, and serial convolution. Because we are not modeling, at least in this model, correlations and interference, we tend to get certain things.
Correlations, Neil.
Yeah, it's all
diffraction does not need quantum theory. Wave theory is plenty good enough for diffraction.
Is actually. Yeah, but,
waves.
I bow to my colleague Peter's expertise in this area, okay, which is way better than mine. He's the real.
Not this Peter. Not this Peter.
No, Peter Thompson. Yes.
Yeah. Neil, is this
so? Jamie's question, does that also relate to the
CERN thesis thing?
That was a very different.
Oh no, that was a far more practical physics issue of how to make calculus more cost effective. Yes.
Okay.
It was not a fundamental quantum mechanical thing they studied. Okay. They were basically worried about the hardware of how does the LHC.
But it was about the particles and all that, and I thought that that's related, but it's not. Okay.
Okay. Let me finish up. More slides will be coming, but not today. Okay. So let me conclude now. So I've given you the basic ideas, but there are many more things. I have not talked about shared resources, congestion, overload management, things like correlations, hazards, slacks. Whenever you get beyond the very simple, so the outcome diagrams that I've presented assume that all the components are basically acting independently, which is the fundamental beginning assumption. But in real systems, that is not always the case when they have shared resources or when there's congestion, which is an example of a shared resource. And there are extensions, so that has to be added. So I have not slides. That I have to admit, I still have to pick the brain of Neil and Peter Thompson more on that. There are some things that are not completely clear on that in my head yet. So that is something that is for future, okay? Another point is that there is a lot of information, slide decks, documentation, coming from PNSol, but nothing as coherent as this talk, I think, but still a lot of things going into many different directions. So that's useful for people interested in this. And finally, there is, I'm giving another tutorial next week in Hackik in Budapest. Maybe I see some of you in Budapest, who knows? And there's a publication that goes into much more in the formal and also the block diffusion algorithm called Mind Your Outcomes. Okay, so let me
I
end
want to
there.
point out that high peak or high PIAC will be twice as long as.
It's twice as long, so I have my work cut out for me. I will try to give even more information. Especially, I will try to touch on shared resources and overloads and slacks and hazards.
Thank you very much.
Okay, thank you.
Is there any question about this tutorial? Okay. So I have just a question.
Sure.
So what about the usability in some sense of the approach? So it seems that
It's at least as useful as anything that UML can do. I mean, it's hard to use. I mean, if you want to do realistic, real-world stuff, at some point you need a tool, of course, huh? But for back of the envelope, you can just use a piece of paper. You can already see if your system, for big systems, a paper and pencil is already using this approach, will already give you insight. But if you really want to do serious design, or you're pushing the envelope, you will need a tool.
Okay, yeah, that's I see that.
Something we want to do. A lot of the basic operations are computation intensive, because the basic data structure is a CDF, which has a huge amount of information in there. Huh? So what can you do? You need to do computation. And deconvolution is very computation intensive. Huh? And then once you do resources, you have correlations. So you're not just doing a computation, you're solving simultaneous equations. So that will require some kind of equation solving system, huh? Probably simple ones, but it's not always continuous. It's often continuous, the equation, to some point. But again, by hand, it's kind of hard, huh?
Okay.
But with computers, this tool can really take advantage of computing power behind the scenes, huh? Make it practical.
We don't still have a tool, but the idea is that we would like to build it.
Yeah, we don't have the tool yet, the potential tool.
That like lay engineers can also use. Now, if you're a tool builder, come talk to us, please.
Yeah, we're looking for PhD students, and we're also looking for funding for PhD students.
Yeah,
correct.
Sure.
Yeah, I mean, IUHK is the company, or now it is called IUG. The company that funded that research, the publication that comes at the bottom. And they have their own team of tool builders and all that, but that doesn't mean that we are not interested in people who can collaborate. In fact, we have, so IUHK has interest in developing tools that helps itself, but ΔQSD is by far larger than just blockchain and all that.
Okay, great.
Thank you.
Okay, thank you again. And for the other people, see you here. Sorry. For the other people, see you here in half an hour with the last tutorial of this day. Okay? Even by this. Okay, see you later.
Thank you.